Question 20 is quite a doozy, actually. It will really make you think. A theoretical isotope with an atomic number Z undergoes the following decays. Beta minus, alpha, alpha, beta positive, and alpha. What is the atomic number of the resulting nucleus? So you can go through it kind of one step at a time, but let's just do the first step, and then you should kind of get the idea of how it works. So if I have an element, it has an atomic number of Z. This is A. And it goes through, so the first one is beta minus decay. So then this would be -1. And this would be a beta particle. And this would be here, here, here. And I've got to figure out what number goes down here, Z, to balance out the equation. And clearly, since over here I just have Z, and now I have a -1 here, I need to put a +1 there, because now it balances out. The -1 and the +1 make 0, and now I've just got Z over here, and I've just got Z over here, and so that balances out. And so it's kind of a counterintuitive thing, because you see beta minus, since you automatically think, oh, it should be Z -1. No, 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 it should be Z +1. And if that's the case, then for alpha decay, when you do alpha decay, I'll do alpha decay, but if you keep doing this process, it just gets really tedious. So now we've got a Z +1, and then it goes through alpha decay. So again, you've got to ask yourself, what do I have to do to balance this? What number do I have to add to this side? Over here, I've got a +1. I've got a 2 here and a 1 there. That makes 3. So let's make those all Z's, so they're like 2's. So the answer is now I put a -2 there, right? Do you see how that worked? So I put a -2 because now over on this side, I've got Z +1. And here I've got, oh, that's way more. That's crazy. Crazy. I said put that so you don't mistake it for 2, and then I put in the wrong one. So over here, now what do we have? Well, we have a 2 here and a -2. They cancel out, and you've got Z +1. So they balance out. So you should start to see the pattern here. And the pattern is, if you've got negative, beta negative, then you add 1. And if you've got something positive, then you subtract. So now let's just do the whole thing. Let's do the whole thing from the beginning. I'm going to do it up here, actually. Here we go. So we have Z. Once you go to beta minus, then it's going to be Z, what do we say? +1. Then you go to alpha, so you're going to subtract 2 from that. If I subtract 2 from that, what do I get? Z -1. Then I go to another alpha. So if I subtract another 2, it becomes Z -3. Beta positive is positive, so I'm going to subtract another 1, and it becomes -4, and then a final alpha, and the answer is Z -6. So I can see a lot of people tripping up on that when I'm putting Z +6, but it's actually minus. Okay, number 21. We've got a particle inside a uniform magnetic field in a bubble chamber, and they want to know the charge to mass ratio. You're given the velocity, the magnetic field strength, the radius. The elementary charge has 2 elementary charges. Pretty straightforward question. We know that the magnetic force equals the centripetal force. And if you've memorized the charge to mass ratio formula, then you can just go right to that step there, and all the information is given to you. Velocity, magnetic field strength, radius. Make sure you change that to meters, or put times 10 to the -3 at the end. And that's all you need to do. Plug those numbers in right here. And that will spit out an answer of C. 4.18 times 10 to the -7. Number 22 says a negatively charged rod is held near a metal sphere. The sphere is then touched with a grounding wire. The grounding wire is removed before the rod is removed. All right, so this is charging by induction. So here we have a negatively charged rod. It's going to be brought near the metal sphere, and if it's brought just near the metal sphere, then what's going to happen? The electrons are just going to go over to this side, but it's going to remain overall neutrally charged. However, once you put a grounding wire on it, then you've provided a path by which the electrons can escape. The electrons can escape. Remember, we're always talking about electron movements, not proton or neutron, electron movement. So you've provided a path, and the electron is going to jump at that opportunity. It's like escaping from jail. They're going to jump at it, and they're going to escape into the earth. Freedom. And then it says the grounding wire is removed before the rod is removed. So the electrons escape, and now all of a sudden it is going to have an overall positive charge, and then you keep the rod there, but you remove the grounding wire. So now you've charged this by induction, and this now has an overall positive charge. Then we can look at all these options here, and it says, listed below are some statements that refer to the procedure described above. So let's just go through this list and discuss each one, whether they're true or false. Protons are attracted and migrate. No. We've just discussed that. We're always talking about electron movement. So anything with protons, you can automatically just scratch off. The grounding wire conducts excess electrons from the sphere to the earth. True. The sphere is left with a final positive charge. Ooh, true. The grounding wire conducts excessive protons. I'm not even going to read the rest of it. The charge, well, that's obviously false. If number 3 is true, then number 5 must be false. Electrons are repelled and migrate to the right side of the sphere. That is false. Oh no, it's true. Electrons are repelled and migrate to the right side of the sphere. Yeah, right side, right here. True. So 2, 3, and 6 are true, but you have to be careful. And so it says the correct statements in order are. So what happens first? 6 happens first. The electrons are repelled and migrate to the right side of the sphere. Then what happens? The grounding wire conducts excess electrons from the sphere to the earth, and then it's left with a final positive charge. So the correct answer for this is 6, 2, and 3. How many more do we have? 2 more. A student places a 10-centimeter candle from a concave mirror with a focal length. The magnification of the image is. Okay, well, we could do a quick diagram for that. Oh, we could not. Well, let's do one. Student places a candle 10 centimeters with. Okay, so this is 15, the focal length, 10 centimeters. So right away, we know we're going to get a virtual image. This is actually similar to that other question on the test. Center. Whoopsie. There's my really rough sketch, and you can see just from that rough sketch that the magnification is going to be significantly bigger. So we're expecting a number that's greater than 1 for the magnification. How are you getting at the magnification? Negative di over do. You have do. You have f. So you need to use this equation to find di, and then you're going to plug it back into this one. So it'll just be 1 over 10 plus, oops, sorry, I'm 1 over di. I'm blowing it here. Let's do that again. Let's do the whole thing. So it's 1 over di equals 1 over f minus 1 over di. 1 over di equals 1 over 15 minus 1 over 10. You're going to get a negative answer because it's a virtual image. It's behind the mirror. And once you solve that, you end up getting negative 30. Which, yeah, looks not bad. Not bad. Negative 30. And then you can plug it into this formula here. And the answer is 3 times bigger, which actually is not too bad at all, based on my diagram. Okay, and last one. The last one is a talks about PET scans, positron emission tomography, and we're just asking if this is a positron-electron annihilation. So a positron meets an electron, it's antimatter particle, and they annihilate each other and become all energy, and they want to know how much energy is released in this reaction. So this is an electron, this is a electron, this is the positron. A positron, make sure you remember that a positron has the same mass as an electron, just the opposite charge. So don't put in the mass of a proton. So we're just going to use E equals mc squared. And the mass here is the combined mass of the electron and the positron. So it's simply 2 times the mass of an electron, because an electron and a positron have the same mass, just opposite charge. Don't forget to square the speed of light, and once you stick that into your calculator, you're going to get an answer of 1.6398 times 10 to the negative 13 joules, but they want the answer in mega electron volts, right? So divide by times 10 to the negative 19, and that ends up giving you 1.02487 electron volts. They want it in mega electron volts, so 1, 2, 3, 4, 5, 6. So the answer is going to be 1.02 mega electron volts. And that concludes the final practice exam. Hope you had fun.